Namaskar and hello dear students. Today we are going to learn about hydrocarbons, that is the chapter 13 of NCERT Chemistry Part 2 textbook. After watching this video, you will be able to classify hydrocarbons into saturated, unsaturated and aromatic compounds. Understand the naming of alkanes according to IUPAC system of nomenclature. Recognize different isomers and methods of preparation of alkanes. Understand the physical and chemical properties of alkanes as well as draw and differentiate between various conformations of ethane. First, let us have an introduction of hydrocarbons. What are hydrocarbons? You might have heard this word while studying the previous chapters. The term hydrocarbon means compounds of carbon and hydrogen only. Hydrocarbons play a key role in our daily life. You must be familiar with the terms CNG and LPG, which are used as fuels. LPG is the abbreviated form of liquefied petroleum gas, whereas CNG stands for compressed natural gas. Petrol, diesel and kerosene oil, they all are obtained by the fractional distillation of petroleum. Coal gas is obtained by the destructive distillation of coal. As you are aware that LPG is used as domestic fuel with the least pollution. Kerosene oil is also used as a domestic fuel. Automobiles need fuels like petrol, diesel and CNG to run. So why we talked about these fuels? Because all these fuels contain mixture of hydrocarbons, which are sources of energy. Hydrocarbons, they are also used for the manufacture of polymers like polythene, polypropylene, polystyrene, etc. Higher hydrocarbons are used as solvents for paints. They are also used as the starting material for manufacture of many dyes and drugs. Thus, you can well understand the importance of hydrocarbons in your daily life. Now, our first discussion is about the classification of hydrocarbons. Depending upon the types of carbon-carbon bonds present in hydrocarbons, they can be classified into three main categories. First, saturated hydrocarbon, second, unsaturated hydrocarbon, and third, aromatic hydrocarbon. Saturated hydrocarbons contain carbon-carbon and carbon-hydrogen single bonds. If different carbon atoms are joined together to form open chain of carbon atoms with single bonds, they are termed as alkanes. On the other hand, if carbon atoms forms a closed chain or a ring, they are termed as cycloalkanes. Unsaturated hydrocarbons contain either carbon-carbon double bond or triple bond, or they can contain both type of bonds. Aromatic hydrocarbons are a special type of unsaturated cyclic compounds. Now we will discuss in details about alkanes. As already mentioned, alkanes are saturated open chain hydrocarbons containing carbon-carbon and carbon-hydrogen single bonds. Methane, which is the first member of this family. Why? Because methane contains only one carbon, so it is being the first member of this family. Methane is a gas which is found in coal mines and marshy places. Now you understand, if you replace one hydrogen atom of methane by carbon and join the required number of hydrogens with both the carbon atoms to satisfy the tetravalency of the other carbon atom, you get CH3CH3, which is known as ethane. Thus, you can consider C2H6 as derived from CH4. And how it is formed? By replacing one hydrogen atom by CH3 group. You can go on constructing alkanes by replacing hydrogen atom by CH3 group. The next molecule which you will find is C3H8, next one C4H10 and so on. These hydrocarbons are inert under normal conditions because they do not react with acids, bases and other reagents. Hence they were earlier known as paraffins. Paraffin is a Latin word where param means little and affines means affinity. The general formula for alkanes is CnH2n plus 2, where N stands for number of carbon atoms and 2n plus 2 stands for number of hydrogen atoms in the molecule. That is why we have seen C3H8, C4H10, how they were derived? Because by the formula CnH2n plus 2, which stands for alkane. According to VSEPR theory, methane has a tetrahedral structure. Figure is displayed on your screen. You can see it is multiplanar, in which carbon atom lies at the center and the 4 hydrogen atoms lies at the 4 corners of a regular tetrahedron. All HCH bond angles are of 109.5 degree. Now let us discuss about nomenclature and isomerism. You are already familiar with the nomenclature and isomerism in organic compounds. To understand it better, we could be discussing few examples in alkanes. First 3 members of alkane series, that is methane, ethane and propane, they only exist in one structure and therefore no isomerism is possible in these structures. But in higher alkenes, they can have more than one structure. Starting from butane, they can have 2 isomeric forms. Taking the example of pentane C5H12, which satisfies CnH2n plus 2. 5 carbon atoms and 12 hydrogen atoms of C5H12 can be arranged in 3 ways. So 3 structures can be drawn. One is continuous chain and 2 is with branch chain, as structures 1, 2, 3 as shown on your screen. Therefore, structures 1, 2 and 3 are isomers of pentane and they possess the same molecular formula. But how they differ? They differ in their structures. They also differ in their boiling points and other properties as well. Since difference in properties is due to difference in their structures, so they are known as structural isomers. It is also clear that structure 1 has the continuous chain of carbon atoms, but structure 2 and 3 have a branch chain. Such structural isomers which differ in chain of carbon atom are known as chain isomers. Thus, you have seen that C5H12 have 3 chain isomers. Similarly, you can draw and explain for butane. It will have 2 structural isomers as we discussed, one in continuous chain and other branch chain. Now you try to draw their structure by yourself. Based upon the number of carbon atoms attached to a carbon atom, the carbon atom is termed as primary, secondary or tertiary and even quaternary. Carbon atom attached to no other carbon atom as in methane or to only one carbon atom as in ethane, they are called as primary carbon atom. Terminal carbon atoms are always primary. Carbon atom attached to 2 carbon is known as secondary. How is tertiary? Tertiary carbon is attached to 3 carbon atoms and neo or quaternary carbon is attached to 4 carbon atoms. If you go on constructing structures for higher alkanes, you will be getting still larger number of isomers. C6H14 has got 5 isomers and C7H16 has got 9 isomers. As many as 75 isomers are possible for C10H22. You have already read about IUPAC nomenclature of alkanes, but we will discuss it further by taking examples of pentane, that is C5H11. Let us write the structures of different isomeric alkyl groups corresponding to the molecular formula C5H11, as you can see in the table shown on your screen. It is shown here 8 isomers are possible for C5H11. Some are linear and some are branched. If it is important to write the correct IUPAC name for a given structure, it is equally important to write the correct structure from the given IUPAC name. To do this, first of all, the longest chain of carbon atom corresponding to the parent alkane is written. Then after numbering it, the substituents are attached to the correct carbon atom. And finally, valency of each carbon atom is satisfied by putting the correct number of hydrogen atoms. This can be clarified by writing the structure of 3-ethyl 2,2-dimethyl pentane by the following steps. First, draw the chain of 5 carbon atoms. Second, give the number to carbon atoms C1, C2, C3, C4, C5. Attach ethyl groups at carbon 3 and 2 methyl groups at carbon 2. Satisfy the valency of each carbon atom by putting requisite number of hydrogen atoms. Thus, we arrive at the correct structure. Now we will learn how to synthesize alkanes synthetically. First is preparation of alkanes. As we are aware that petroleum and natural gas are the main sources of alkanes. However, alkanes can be prepared by some of the methods which we are going to discuss. First, alkane can be prepared from unsaturated hydrocarbons, whether alkene or alkyne. You can see some of the reactions on your screen. Hydrogen gas adds to alkenes and alkynes in the presence of finely divided catalysts like platinum, palladium or nickel to form alkanes. This process is called hydrogenation. Why hydrogenation? Because hydrogenation means addition of hydrogen to multiple bonds. It can be alkene or alkyne. These metals absorb hydrogen gas on their surfaces and activate the hydrogen-hydrogen bond. Platinum and palladium catalyze the reaction at room temperature, but relatively higher temperature and pressure are required with nickel catalyst. Second is preparation of alkanes from alkyl halides. Alkyl halides accept fluorides. On reduction with zinc and dilute hydrochloric acid, they give alkanes. For example, the reactions shown on your screen. Chloromethane on reaction with hydrogen in the presence of zinc and hydrogen ions, it gives methane plus HCl. And similarly is the second reaction. Another example is alkyl halides on treatment with sodium metal in dry ether. Dry ether means which is free from moisture. Used as solvent give higher alkanes. This reaction is known as Wood's reaction and it is used for the preparation of higher alkanes containing even number of carbon atoms. For example, CH3Br combining with CH3Br in the presence of sodium atom and dry ether as solvent, it gives ethane. And second example you can also see considering bromoethane. What it gives as the end product? It gives butane. Now the third preparation is of alkanes from carboxylic acid. Sodium salts of carboxylic acids on heating with soda lime. What is soda lime? Soda lime is mixture of sodium hydroxide and calcium oxide. It gives alkanes containing one carbon atom less than the carboxylic acid used for the reaction as reactant. This process of elimination of carbon dioxide from a carboxylic acid is known as decarboxylation reaction. For example, sodium ethanoate on reaction with sodium hydroxide in the presence of calcium oxide and heating it gives methane and along with the side product as sodium carbonate. The second method for the preparation of alkanes from carboxylic acid is Kolb's electrolytic method. An aqueous solution of sodium or potassium salt of a carboxylic acid on electrolysis gives alkane, which contain even number of carbon atoms at the anode. You can see an example of Kolb's reaction on your screen, that is sodium acetate on reaction or electrolysis with water gives ethane plus carbon dioxide plus hydrogen plus sodium hydroxide. This reaction is supposed to follow the path shown on your screen. Sodium acetate is a strong electrolyte which completely dissociates into acetate and sodium ion in water. Therefore, sodium acetate is a strong electrolyte, completely dissociates into acetate and sodium ion in water. Therefore, sodium acetate giving acetate ion and sodium ion in the presence of water. On electrolysis of aqueous sodium acetate, acetate ion gives off an electron at anode, thereby forming acetate free radical which is unstable and converts to methyl free radical and carbon dioxide gas is released. The reaction at anode you can see on your screen. Then two methyl free radicals combine to form ethane, and at cathode water accepts an electron releasing hydrogen gas. Therefore, it is clear that methane cannot be prepared by this method. Now we will talk about physical properties of alkanes. Alkanes are almost non-polar molecules because of the covalent nature of CC and CH bonds and due to very little difference of electronegativity between carbon and hydrogen atoms. They possess weak van der Waals forces. Due to the weak forces, the first four members C1 to C4 are gases. C5 to C17 are liquids, and those containing 18 carbon atoms or more, they are solids at 298 Kelvin, or we can say room temperature. They are colorless and odorless. Petrol, which is a mixture of hydrocarbons and is used as a fuel for automobiles. Petrol and lower fractions of petroleum, which are used for dry cleaning of clothes to remove grease stains. On the basis of this observation, what do you think about the nature of greasy substance? You are correct. If you say that grease is mixture of higher alkanes, that is non-polar, and hence they are hydrophobic in nature. It is generally observed that in relation to solubility of substances in solvents, polar substances are soluble in polar solvents, whereas non-polar ones in non-polar solvents, which satisfies the philosophy that like dissolves like. Boiling point of different alkanes. They show a steady increase in boiling point with increase in their molecular mass. This is due to the fact that intermolecular van der Waals forces increases with the increase of the molecular size or with the surface area of the molecule. You can make an interesting observation by having a look on the boiling points of these three isomeric pentanes, with pentane or 2-methylbutane and 2,2-dimethylpropane. It is observed that pentane, having a continuous chain of 5 carbon atoms, has the highest boiling point, which is 309.1 Kelvin, whereas 2,2-dimethylpropane, it boils at 282.5 Kelvin. So, we conclude with the increase in number of branch chain, the molecule attains the shape of a sphere. This results in smaller area of contact and therefore weak molecular forces between spherical molecules, which are overcome at relatively lower temperature. Now we will discuss about chemical properties of alkanes. The first one is substitution reactions. One or more hydrogen atoms of alkanes can be replaced by hydrogens. Now we will discuss about chemical properties of alkanes. The first one is substitution reaction. One or more hydrogen atoms of alkanes can be replaced by halogens, nitro group and sulfonic acid group. That is why it is termed as substitution reaction, because we are replacing hydrogen atom by some functional group. Halogenation can take place either at higher temperature or in the presence of diffuse sunlight or ultraviolet light. We are using such harsh conditions because it is difficult to break carbon-hydrogen bond as they are stronger in nature. These reactions in which hydrogen atoms of alkanes are substituted are known as substitution reaction, which we have already discussed. Is an example chlorination of methane. Along with the mechanism of reaction is shown on your screen. As you can see, methane plus chlorine in the presence of ultraviolet light, giving CH3Cl plus HCl. CH3Cl again combines with chlorine in the presence of ultraviolet light. It gives CH2Cl2 plus HCl. So it keeps on substituting hydrogen atoms, and at the end we get CCl4 plus HCl. It is found that the rate of reaction of alkanes with halogens is highest for F2 and lowest for I2. Rate of replacement of hydrogens of alkane is tertiary, secondary, primary. Fluorine is too violent to be controlled. Iodination is very slow and a reversible reaction. It can be carried out in the presence of oxidizing agent like HiO3 and HNO3. These oxidizing agents convert back the Hi formed into I2, hence prevent the backward reaction as shown in the screen. Halogenation is supposed to proceed via free radical chain mechanism involving 3 steps, namely initiation, propagation and termination. Now let us see the mechanism of the reaction in detail. First step, initiation. The reaction is initiated by homolysis of chlorine molecule in the presence of light or heat. The Cl-Cl bond is weaker than the Cc and CH bond, and hence it is easiest to break as shown on the screen. Cl-Cl in the presence of light undergoing homolysis gives 2 chlorine free radicals. Second step is propagation. chlorine free radicals attacks the methane molecules and take the reaction in the forward direction by breaking the CH bond, which generates methyl free radical with the formation of HCl. The methyl free radical thus obtained attacks the second molecule of chlorine to form the CH3Cl with the liberation of another chlorine free radical, which is formed by homolysis of chlorine molecule as shown on your screen. The chlorine and methyl free radicals generate in the propagation step of the reaction, steps A and B respectively, and thereby set up a chain of reactions. The propagation steps A and B are those which directly give principal products, but many other propagation steps are possible and may occur. Two such steps which explain how more highly halogenated products are formed as given on your screen, as like CH3Cl plus Cl free radical giving CH2Cl radical plus HCl, or further step CH2Cl free radical combining with ClCl gives CH2Cl2 plus Cl free radical. Now we will discuss the last step, that is the termination step. The reaction stops after some time due to consumption of reactants and or due to the following side reactions. The possible chain terminating steps are in three steps A, P and C, which you can see on your screen. First, ClCl free radical combining to form Cl2. Second, CH3CH3, that is the two methyl radicals combining to form ethane. Or third can be CH3 radical and Cl radical combining to give CH3Cl. Though in third step CH3Cl, which is one of the product formed, but free radicals are consumed and the chain is terminated. The above mechanism helps us to understand the reason for the formation of ethane as a byproduct during chlorination of methane. Now we will discuss about the second chemical property, that is the combustion reaction of alkanes. Alkanes on heating in the presence of air or oxygen are completely oxidized to carbon dioxide and water with the evolution of large amount of heat. For example, methane combining with oxygen giving carbon dioxide plus water. The general combustion equation for any alkane is shown on the screen, where n moles of CO2 and n plus 1 moles of H2O are formed. The balanced chemical equation is appeared on your screen. Now we will discuss about the oxidation of alkanes. We can call it as controlled oxidation. Alkanes on heating with a regulated supply of oxygen at high pressure and in the presence of suitable reaction conditions and catalyst give a variety of oxidation products as shown in the reaction on the screen from 1 to 3. First, methane combining with oxygen in the presence of copper catalyst and certain reaction conditions, it gives methanol. Second, methane recombining with oxygen in the presence of MnO2 as catalyst giving HCHO, that is methanol. Third reaction in which ethane combines with oxygen in the presence of manganese as catalyst, it gives acetic acid, that is, or ethanoic acid, which we can say. Fourth, generally alkanes resist oxidation, but alkanes having tertiary hydrogen can be oxidized to corresponding alcohols by potassium permanganate. For example, 2-methylpropane oxidizing in the presence of potassium permanganate. It gives 2-methylpropane-2-ol. Now, fourth type of chemical reaction shown by alkanes is isomerization. N-alkanes on heating in the presence of anhydrous aluminium chloride and hydrogen chloride gas isomerized to branch chain alkanes. For example, when N-hexane is heated in the presence of anhydrous AlCl3, major products are shown on your screen. They get isomerized to form 2-methylpentane and 3-methylpentane. Now we will discuss about fifth property, that is aromatization. In alkanes having 6 or more carbon atoms on heating to 773 Kelvin at 10 to 20 atmospheric pressure in the presence of oxides of vanadium, molybdenum or chromium supported over alumina get dehydrogenated and cyclized to benzene and its homologous. This reaction is known as aromatization or reforming as given in the reaction on the screen. In the given example, N-hexane gets cyclized and aromatized to benzene on reaction with chromium oxide or vanadium oxide or molybdenum oxide. Another chemical reaction is with steam. Methane reacts with steam at 1273 Kelvin in the presence of nickel catalyst to form carbon monoxide and hydrogen. This method is used for industrial preparation of hydrogen gas. Reaction shown on your screen says methane plus H2 reacting in the presence of nickel gives carbon monoxide and hydrogen. Now we will discuss about pyrolysis. Higher alkanes on heating to higher temperature decompose into lower alkanes and alkenes. Such a decomposition reaction into smaller fragments by the application of heat is called pyrolysis, or it can be called as cracking. It has not been possible to separate and isolate different conformational isomers of ethane because of their rapid interchange in different conformations. Now with this, let us conclude what we have discussed today. We studied about classification and naming of hydrocarbons. We have also discussed about the physical and chemical properties of alkanes, different isomers of alkanes, and methods to synthesize alkanes. We will discuss further about alkenes in the next lecture. Be safe and keep learning and exploring. Thank you.